Hi everyone, welcome back to Math Together Canada. This is the second part of our special AMC 8 series featuring Andy, a good friend of MTC. In this video, he'll be solving questions 11 to 15 of the 2024 AMC 8, tackling the harder problems from this contest. We're very grateful to Andy for sharing his time and passion for math with all of you. If you also love math and would like to contribute by recording a problem-solving video, we'd love to hear from you. You can reach us at contact@mathtogether.ca. Let's work through these problems together.
Alright, the coordinates of triangle ABC are A57, B11, 7, and 3, C1 provides greater than 7. And the area of triangle ABC is 12. What's the value of y? So quickly we can just find the base length to be 6. And since the area is 12, we know that this height over here has to be equal to 4. And then we have this equal to 3. We have the original y equals 5, so y just equals to 9. Since 9 minus 5 equals to 4, 4 times 6 divided by 2 equals to 12, and that complies with everything that we have so far. Wait, hold on. Lines roots. Wait, hold on, sorry, I'm a little blind. I read the S digit as row 1. I thought that should have been correct from how I subtracted 11 from 5. Sorry. So 6, yeah, the 7 says 7 plus 4 equals to 11. And that just equals to D. Yeah, my bad. Problem 12. Rohan keeps a total of 90 copies in 4 fish tanks. There's one more copy in that second tank than the first tank. There are 2 more copies in the third tank than the second tank. There are 3 more copies in the fourth tank than the third tank. So let's just do everything. This is actually similar to the problem that we did about the marbles. You just want to write everything in the copies in the first tank. So copies second tank 2 n, or actually I'll just say n2 equals to n1 plus 1, n3 equals to n2 plus 2, n4 equals to n3 plus 3. And now we have just extend this, so then n3, we substitute our value of n1 plus 1 in for n2, n1 plus 3, and n4 we substitute our value of n3 in, n1 plus 3, so equals to n1 plus 6. So adding them all, we have n1 plus n1 plus 1 plus n1 plus 3 plus n1 plus 6, which equals to 4n1 plus 10. And then that gives us equal to 90. So 80 equals to 4 and 1, and 1 equals to 20, and we have n4 over here equals to n1 plus 6. So 20 plus 6 is 26, which gives us E. Alright, problem 13. Buzz Bunny. Oh, I took that screenshot. Buzz Bunny is hopping up and down the set of stairs, one step at a time. In how many ways can Buzz Bunny start on the ground, make a sequence of 6 hops, and end up back on the ground? Well, so what comes over here is that we must have 3 times Buzz Bunny goes up and 3 times Buzz Bunny goes down, right? Which basically means we have to arrange the characters up and down. But we must always have more ups than downs. So like we can't have like down, down, up, 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 down. That just wouldn't make sense because it starts on the ground already, right? So uh in total we just want to find how many unique orderings, right? Such that there, well, for each ordering we have like a certain rule. Like for each prefix of the order, there are more ups and downs. But this one also corresponds to like this arrangement, right? So what I want you to see is just for each up arrow here is replaced by a down arrow here. But this arrangement is invalid while this arrangement is going to be valid. So what we can do here is that we have 3 ways to arrange or just pick out numbers of orders of ups and downs, which equals to 6 times 5 times 4 divided by 6, which is equals to 20. And then we have orders like, and we want to find the orders in which it is uniquely determinable to um hmm, have it be down up. How should I? Well, basically at any point within the sequence, you can't have more down symbol actually. So actually, yeah, there's a little bit of a better way to count this. We can just count this using casework, right? So let's just say that the first time the body goes up one jump before going down, and then it goes up one jump again before going down, and then the third time one one. So this just corresponds to ordering 1 1 1. So we're just basically finding the amount of order sets here, right? Such that all of the elements add up to 3. So 3 elements in the set, we have 1 1 1. 2 elements in the set, we have 1 2 2 1. 1 element in the set, you just have 3. And for each of these, like this, one up, one down, or actually for these ones, right? This one just be up, 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 down, down. This one will be up, down, up, down, up, down. This one will be up, down, down, up, down. And this one will just be up, 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 down, down, down. And hmm. If it helps us, yeah, wait. It doesn't always have to reset afterwards, though. If you end up at like one stair, so is there a neater way to count this? Well, we always know that it has to be ending off at a D. So we can just like move the D to the side. We have 2 Ds left and then 3 ups. And then we're just going to have up, 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 or just go up, up, up. And then we can put the 2 downs, one down here, one down here, or we can put them both after, like that. Well, the only invalid one here would just be up, down, down, up, up. We can just bypass the first step as like another thing, right? So that's just 4 choose 2. 4 times 3 divided by 2 equals to 6. And then this order is not good, so -1 equals 5. So which one was I missing here? Okay, up, down. Oh, wait. No, I was missing up, up, down, down, down. Oops, okay. That was one last missing. So yeah, the answer is D here. Oops. Alright, problem 14. What's the distance of a short strip from A to C? Alright, so this is just minimum distance problem. We solve this using Dijkstra. So we just have our priority queue here, right? We have so we just hand the edges for x and then m. So those are the only two edges that we can have. So we have 5 to x, and then actually let me just erase the end of this priority queue. 5 to x, so that's our first edge over here, and then 8 to m, that's our second edge over there. And then this one's just small, so we take it over q. So x nearest distance to x equals to 5. And then we add in the next edge over here that we consider, which is just 2. So 5 plus 2, we get the distance to minimum distance to m equals to 7. This one's basically irrelevant now, this item. 7, we can just write down there. And this is the next smallest edge that we can consider, right? So the distance to y, actually, we have two choices, 15 over here, 13 over here, 13 is smaller, so we just write that as 13. And then 7 plus 14 plus 21 versus 5 plus 13 is 18. We get that, and this is just smallest. 18 plus 8, 7 plus 25, which equals to 32, 18 plus 10, which equals to 28, and 13 plus 7, which equals to 30, so we get the answer as 28. A is the solution to 14, 15. Another large fly bug represent distinct digits. Suppose fly phi is the biggest number that satisfies the equation. 8 times fly phi equals fly bug. What's the value of FLY plus BG? So the thing here is that they are all distinct digits, but 8 times that equals to that. And then we have that just basically means it has to be less than 125,000 or fly phi, right? Because if it's equal to 125,000, so 125k times 8 equals to 1 million, which just adds in another digit, which makes bug impossible. So this basically makes us certain that FLY, and being the greatest, right? The first digit F must equal to 1. And then the second digit, right? It has to be distinct. 2 is definitely possible. So L equals to 2 or 0 here. It can't be 3, by the way, because I'll just see that. And Y can be basically anything from that's not equal to 1. That is also not equal to L, but anything else that works. So we also notice that BUG is like kind of like the same pattern, right? And 8 times FOY, we just get B equals to 8, so B must also equal to 8 over here, which leaves UG out. And that means that we also can't carry digits back there. So for example, if U were equal to like, or I mean if L were equal to 2, 2 times 8 would carry a digit over to the B, because it equals to 16, and then there's be a remaining digit here, and that just be bad, which basically means that our L has to be 0. And then now we just have to think of our Y. Well, we can just put 1, 0, Y, 1, 0, Y times 8 here, just to speed things up. So we have 8, 0, 8, Y here, and 8, 0, 8, Y. Now we notice that like 8Y can have like digits passing over it. And it basically really doesn't matter how we set Y. As long as we set it as big as possible, digits pass over will still be the same. So we can, if Y equals to 9, we get actually 8. 9 times 8 equals 72, 872. And the value of 5 plus above, which is equal to 109 plus 872 equals to 881 plus 100, which equals to 981. And that will not be a solution. Wait. Yeah. Wait, no. So actually, we can't have 2 times 8 because material just consistent. So 1, 2, 9. We can first try that out. But that's just going to be too big. So 1, 2, 5 is also too big. 1, 2, 4 is our next best bet. So we multiply that by 8, we get 9. Here we get remaining 6. And then 4 times 8 is 32, so 2. And then another 9 here, but that doesn't work. So we try 123. 123 will give us 3 times 8 equals 24. So 8. And then 984, 984, and those are all you need. So 984 plus 123 actually gives us 7, 0, 1. Wait, what? Oh my goodness, I can't add. 1107. Okay, C.
That wraps up part 2 of our AMC 8 series. Thanks for following along as Andy solved questions 11 to 15. These problems definitely start getting trickier, but we hope seeing the thought process helped you understand them better. Huge thanks again to Andy for sharing his time and strategies with us. If you're enjoying this series, make sure to check out part 3 where he tackles questions 16 to 20. And if you're also a math enthusiast who'd like to create a video of your own, we'd love to feature you. Reach out to us at contact@mathtogether.ca. See you in the next one, and keep having fun with math.